So can anyone recollect what we did in the last class?
And back propagation, we were finding the delta.
So in back propagation, we are finding the delta of which layer, sir?
Output layer.
Output layer. So what we did is that we saw how to find out the deltas for the output layer. And what else we saw in that?
We saw the error surface with respect to one prediction fixed and where other remains a constant, vice versa, and finally both varying things.
Okay, we also saw about, we discussed how the gradients are changing in the error surface and how from that we calculated the deltas for the output layer. So in today's class, what we will do is that in the last class, we learned how to find the deltas for the output layer. In today's class, we will find how using these deltas,
Weights.
we can change the weight. So tell me one thing, how we can change the net neurons output? So what if I change the neurons output will change?
Delta value will change.
No. Just assume that we need to change the neurons output. So what if I do, the output will change?
You can change the weight.
Yeah, we can change the weight and then simplest answer. By changing the inputs. Or you can test previous layer output. So if you need to change the neurons output, you need to change the previous layer's output, which is going to be the input for the current neuron. Or else we need to change the weight, which is connecting the previous layer to the current layer. So by these two things, we can change the neurons output. Let us assume that you have one neuron, which is called as C from the tiny neural network, which we saw in the last class. We assume we have two neurons. For time being, we are assuming only two neurons. One is A and the other one is C. So these neurons are the summation of the previous layer outcomes. This is connected to C by the weight called AC. A naught is the outcome which is coming out of the neuron A. And let's assume the change in the output neuron is B. So what is V here? V is nothing but A naught into AC. So A naught is so you have two neurons. If you assume previously we saw that in the tiny neural network, A is this and C is this. So A, we are looking only at the connection between A and C. So this is A and this is C. So what happens in the neuron A? We get input from the previous neurons. So all the input from the previous neurons gets added up, and we don't have an activation function here. For the time being, we are ignoring the activation function. So what happens? All the summed input comes as an output. So this is A naught. And the A naught is multiplied with the edge weight. The edge weight here is AC. And that goes as an input, or that goes as a value to neuron C. So the change in the output which comes here is B. For time being, we assume that this connection is not there. Only the connection from A is existing. So this connection is not there. So whatever change which has happened at C is nothing but is equal to A naught into AC. Let us assume if V changes for any reason, we know that the output of the C will change by V as well. So whatever change, since the change in C is V, we can consider that the network error will change by V into C delta. So last time what we saw that we saw the change in the outcome into delta value will give you the change in the network error. So here a change in the outcome is V. So V into C delta will give you the change in the network error. So there are only two ways the value of V can change. So how the value of V can change? Either you need to change A naught or you need to change AC. So either you have to change the weight or you have to change the outcome of A. So since the outcome of A is computed by the neuron automatically, there is nothing much we can do with that one. So we cannot adjust that weight. So what we can do is that what is the thing which is easy to adjust, because it all depends on the previous neuron connection. So this one we cannot do much, but we can alter the weight to see how much change is happening here. So let's modify this weight. So we have two neurons. These neurons are connected by the weight AC. This is A naught. You have connections from the previous layer, and this is V. So this is what we have seen before. Now what you are doing is that you are adding a value ACM. So that we wanted to change V. So let's assume that what is the change in the outcome? So previously the V value was A naught into AC. Now the value is A naught into AC plus ACM. So what is the change in the outcome? The change in the outcome is A naught into ACM. That is the difference. So if you look at it, this is the change which is going into C. So this is the change in the outcome which is going into C. And this will get multiplied by the value C delta. A naught into ACM will get multiplied to C delta to find the change in error.
Ma'am, this A naught into AC plus ACM means you should have two values, no? A naught into AC plus A naught into ACM.
Yeah, we have two values, but this is change in outcome. So this is your previous value of V. This is your current value of V. Did you understand this one?
Mm-hmm.
So here, if you look at it, V is given by A naught, A naught is coming, A naught is getting multiplied by AC, and that is V here. Now what we are doing, we learned that how we can change the value of V. Either we need to change the weight or you need to change the outcome. So we cannot do much with the outcome. So what we are doing is that we are changing the weight. So how are we changing? We are adding a weight called ACM. So now V value is A naught into AC plus ACM. So that is the current value of V. So what is the difference between these two? So
Yes, ma'am.
So current value difference the previous value. So current value is A naught into AC plus A naught into ACM. Previous value is A naught into AC. So this will subtract and we will get only this one. So this is the change in the outcome.
Yes, ma'am.
So change in the outcome into network delta, the neuron delta is nothing but the change in the network error. So A naught into ACM into C delta will give you the change in the network error.
Change in network error for C, right, madam? For C neuron.
Yeah, for the C neuron. No, change in the network error for the whole network. Right now, our whole network is A and C only.
Okay, okay.
So for this network, what is that. So that only I have written. Otherwise, I would have written change in the network. Change in the error for neuron C. But this is the change in the error for the whole network. Right now, our network is only A and C. So we are just assuming this connection to be our network. So now this is our network. We have got the change in the network error. So let us assume that if ACM, the weight, if the weight is going to be 1. So what we have concluded is that the change in the network error is A naught into ACM into C delta. So now let us assume that we increase the weight by ACM. So previously some weight was there. AC, some weight AC was present. We are adding some new weight ACM and this value be ACM is equal to 1. So how much the change in error will be? Then the change in error will be A naught into 1 into C delta, that is A naught into C delta. Suppose if you are adding the weight ACM is equal to 2, then change in error is, what is change in error?
A naught into 2 into CS.
A naught into 2 into CS, that is 2 times A naught into C delta. This is delta, not S. So if ACM is equal to 0.5, or you can say 1/2, it is reduced by half. Then change in error is half the times A naught into C delta. So how much ever you are adding, so that much amount A naught into C delta will increase or decrease. So if you add 0.5 to the weight, we will get half as much of A naught C delta. If you are adding 1, we will get the whole of A naught to C delta. In other words, we can say that if you want to increase the error by 1, then we should add A naught into C delta to the weight. This is other way of saying. So if you want to go if you want the error to go down, then we can reduce the error by 1. So instead of adding, what we will do, we will subtract the value A naught into C delta from the weight. So to subtract, I can tell to subtract 1 from the error. So what we need to do? We need to subtract A naught into C delta from AC. Did you get this point?
No, madam.
So what you didn't get?
This last thing, to subtract 1 from the error, we subtract. Can you explain?
So till this it is clear?
Yeah, clear, madam. Till this.
So the change in error is how much the error is going to change.
By
So
how much
previously,
you
when you are having 1, when you are adding weight 1, the change, how much the error changes? The error changes by A naught into C delta.
Yes, madam.
So next time what you are doing, you are changing the weight by 0.5. So when you change the error by 0.5, the error is changing by half into A delta. Sorry, half into C delta. A naught into C delta.
Yes, ma'am.
So according to the weight, the error is changing. So
yes,
instead of, so I can put it in the reverse way. So if I put it in the reverse way, I will say that if we want to increase the error by 1, we should add A naught into C delta to the weight.
Okay, got it.
Got it?
Yes,
so I'm putting it in the other way around. So if weight is 1, the change in error is A naught into C delta.
Yes, ma'am.
So if I want the change, if I want to increase the thing by 1, then I should add a weight of A naught into C delta. I'm putting it in ulta.
Yes, ma'am. Yes.
This is other way of saying it.
Okay.
So if I want to, this is like weight will increase by A naught into C delta, the error will be 1. So if I want to reduce the weight, not increase the weight, if I want to reduce the error, then what I need to do is that I need to put a subtract sign before it.
Yes, ma'am.
So that's what, to subtract 1 from the error, we need to subtract A naught into C delta from AC.
Yes, ma'am.
So if you want to add, it is positive sign. If you want to subtract the error, if you want to reduce the error, we need to subtract from the weight. So you can So this is change in the weight. If the change in the weight is going to be, remember this is only change in weight. I'm not saying the actual weight. So if the change in weight is A naught into C, the error will change by +1. If the change in weight is minus A naught into C delta, the error will change by -1. So we can get it. This figure shows that every change of A naught into delta in the weight leads to the corresponding change of 1 in the network error. And by subtracting that value, it leads to the change of -1 in the error. Is it clear?
Yes, ma'am.
So now let us see it pictorially. So let us assume this is neuron C. The output from the neuron C is shown by the right side pointing arrow. This is C naught is the output which is coming from the C neuron. And C delta is shown by the pointing arrow towards the left. So from the same neuron, if the arrow is pointing towards the right, it is the outcome which is coming from it. If it is pointing towards the left, it is the delta value which is coming from it. So now let us understand that we have seen that how by changing the weights, the errors are reducing or increasing. So now let us understand this pictorially. So if you look at here, we have two neurons. We are looking only at the connection between these two neurons, A and C. The arrow is coming towards the left. So this is C delta. The arrow is coming here pointing towards the right. So this is the outcome which is coming from the neuron A. So what we are doing, we wanted to decrease the error by 1. So if you want to decrease the error by 1, then what we need to do, we need to subtract the outcome which is coming from this one multiplied by C delta from the current existing weight. So we need to multiply both the things. So we need what we learned. This is what we learned. So I need to reduce the weight by error by 1. So I have to subtract the existing weight by A naught into C delta. So A naught is coming from here, C delta is coming from here. I'm multiplying it by -1 because I want to reduce the error by 1. So I'm multiplying it. And then what I'm doing it, I have to subtract it from the existing weight. The existing weight is AC, which is connecting these two. So I'm subtracting from the existing weight and then updating the value. So the current value is AC minus A naught into C delta. Is it clear?
Yes, ma'am.
So we are updating the value of the weight AC. We start with the output A naught from the neuron A and the delta C from neuron C, multiply them together, and then we would like to subtract this from the current value of AC. To show this clearly, instead of subtracting sign, we are multiplying it by the product of -1 and then we are adding it to AC. So this arrow is nothing but the update step. We are updating the current weight AC by this value. So this is this from this subtraction, it is getting added up here. This is how the network will learn. Is it clear how by changing the weights the errors are changing? So this is how the network will learn, and this is why this is how deltas are used in changing these weights. Did you understand how the delta is involved in changing the weights?
Ma'am, delta alone, I mean, I have doubt, ma'am.
What
Delta.
doubt?
Ma'am, could you just go to this previous thing that previous page, ma'am? No, this the previous. Yeah. Okay. So in this change, the CS is from the delta of that next neuron. Subs
So
okay. Oh.
we have two neurons. So this was this was our neural network A, B, C, D. So we are looking only at this link. In this link, only A and C is present. So we are considering only this link, and then we are taking it. So if you take it, this is the outcome. Outcome of A is A naught, and these A and C are connected by the weight AC. And the value which is arriving at the C is given by the letter V, which is a temporary variable, which is given by the letter V. Is it clear till this point?
Yes, yes, sir. Yes, ma'am.
So we are only looking at, remember, for understanding purpose, we are only looking at
A and C.
this link, A and C. So in the last class, what we did, we understood how to calculate C delta, which is the delta for the output layer. So we understood how to calculate C delta. So now we have C delta in our hand. C delta is present here. So now we know that A
C
naught is
delta
the outcome of
quadratic cost function, the label minus output,
So
or
it can be anything.
the slope or the label minus the output.
Based on the error function you use, it can be anything.
Okay.
So we have calculated C delta now. So let's not go back to that one. For a time being, you understand that we have calculated C delta and it is there. So based on what error function you use, the formula would vary for that one. So for let us assume we have used quadratic cost function, and that is a difference between the label and the what to say output.
CO.
So we have got that one C delta. So now the whole purpose of today is to understand how using C delta we can change the weight. The overall goal of the entire network, what is learning? Learning is changing the weight so that our error will be 0. We want to achieve, our goal is to make the error 0. How to
Okay.
make the error 0 by learning the weights. So we
Mm.
have to change the weight. So now today we are going to learn how by changing the, how delta is helpful in changing these weights.
Yes, ma'am.
Is the connection clear?
Yes, yes, ma'am.
So,
Okay.
so now for that purpose, we are not looking at the entire, we will look at the entire neural network, but for time being, we are understanding only one link, only two neurons, and we are looking at it. So this V value is given as A naught into AC.
Yes, ma'am.
So V value is this one. So what will happen to the change in the network error? So change in the network error is outcome of this one, outcome of C, because we don't have any other outcome here. So what we have is only C. C is the outcome. So C change in outcome into C delta will give you the change in the network error. So
Yes,
how
ma'am.
we can change the value of V? We have to change either A naught or we have to change AC. A naught is the outcome of neuron A, or AC is the weight which is connecting between A and C. So either by changing the weights or by changing the outcome. We cannot do much with the outcome, because it is a combination of the previous neurons, which is previous neuron layers. So we cannot touch this neuron, but we can change the weight and we can change the V. Thereby we can bring the change in the network error. So what
Ma'am,
we have to
uh,
bring a
sorry to interrupt.
hmm.
So this P is change in the output of C. So we can bring the change in output of V by only changing the adding weight to the adding component to the weight. Am I right, ma'am?
Yeah, by adding component, we can also bring change by changing the inputs. Input in sense A naught.
Yes, ma'am.
That is
Okay.
also possible. But now we are not looking at the further neurons. So we are just looking at the local level. The
Okay.
local level, we can change the weight and then we can bring in the change in the outcome of C. Thereby we can bring in the change in the network error because they are all related.
Yes, ma'am.
So once. So now the change in the network error is given as V into C delta. So now, okay, now we have to bring a change in the network error. So we have to reduce the error. So what we have to do, we have to change V. So I'm changing the weight. So what I'm doing is that I'm changing by adding ACM to the weight.
Yes, ma'am.
So if I add ACM, what will happen to V? V is nothing but A naught into AC plus ACM.
Yes, ma'am.
So this is the current value of V. The previous value was A naught into AC. So this is V is nothing but the value which is entering into the C. That is V. So previously the outcome was A naught into AC. Now the outcome is A naught into AC plus ACM. So what is a change in the outcome? Change in the outcome is difference between the current and the previous value. So the difference between the current and the previous value is A naught into ACM.
Yeah.
So now the change in the network error is given by A naught into ACM into C delta.
Yes, ma'am.
So change in the outcome into delta value will give the change in the network error.
Yes, ma'am.
So now what we are going to do is that we are playing with a small analogy and then we are going to understand that. So by changing the weights, so whole process is that by changing the weights here, we can change the network error, isn't
Yes.
it?
Yes, ma'am.
So we are going to see how it is possible with some small examples. So when weight is equal to 1, what happens to how much the error changes? The error changes by A naught into AC. So
Yes,
when
ma'am.
the weight is 2, the error changes by 2 into AC naught. So when the weight is half, the error is reducing. So, so we can say otherwise, when weight is equal to A naught into C, when weight is equal to A naught into C, the change in error is going to be 1. So the error is going to increase by 1.
Yes, ma'am.
When we add, when the change in the weight is 2 into A naught by C, the error is going to increase by 2. Suppose if the weight is going to be minus A naught into C, the error is going to decrease by 1. The change in error is going to be decreased by 1. So to subtract 1 from the error, so to decrease 1 from the error. So if you want the change of error to be minus 1, then we need to subtract A naught into AC from AC. So that is what is explained in this figure. So the change in the weight is A naught into AC. The change in the network error will be 1. So if the change in the weight is going to be minus A naught into AC is the change in the weight, then the change in the network error is minus 1.
Yes, ma'am.
So now what we are doing is that, so we are looking at the conventions. So if an arrow is pointing from the towards the right, it is the outcome which is coming from the neuron. For any neuron, let it be A or C or B or D, for any neuron, if the arrow is pointing towards the left, it is the outcome which is coming from the neuron. If the arrow is pointing towards the left, it is the delta value which is coming from the C neuron. So now what we understood, so if the change is going to be, if the change is going to be minus A naught into AC in the weight, then the error will decrease by minus 1. So we want to decrease the error by minus 1. So what I'm going to do, I'm going to subtract minus A naught into AC from the AC value.
Yes,
So
ma'am.
how to see this one pictorially? So we take the A naught value. So this is A naught into C delta. So A naught comes from A, C delta comes from C.
Yes, ma'am.
Both gets multiplied by minus 1 because we have a minus here. And then we need to add it with AC. And then update the AC value, current AC value. First it was AC, then it was this value. So we need to update the AC value with this value. So by
Okay.
doing this one, you are seeing that how by using C delta, we are able to change the weights. So that was our whole objective today. So
Yes.
how by using the C delta value, we can change the weights. Previously, we saw that the change in the outcome, how the change in the outcome and the weights can change the error.
Yes, ma'am.
So now what we are understanding is that how by changing the delta, we can change the weight, thereby we can impact the error.
Yes, ma'am.
Is
Got
it
it.
clear?
Yeah,
For
clear.
others? Others, is it clear? Or else should I explain once more?
No, it's clear. Thank you.
Okay. Any questions? I'll give you 1 minute. Just look at it and let me know. Because only if this is clear, we can go to the next session. So this is how our network learns. So this tells us how to change the weight to bring down the error. So this diagram, if you see, it says us that we need to reduce the error by 1. So we need to add minus A naught into C to the value of A. So if we change the weight for both the neurons, let us assume that we have both the neurons C and D. So we need to reduce the error by 1. So we would expect, so C will reduce 1, D will reduce 1. So in total, the network error will be reduced by minus 2. So this is because the neurons are sharing the same layer, but they do not rely on each other. So if you look at here, so here C and D are in the same layer. They are not sharing the output, but same A is coming to D and same A is going to C. So suppose if you change the weight between A and C, this will reduce the error by 1. If you change the weight between A and D, this will reduce the error by 1. So totally network 1 plus 1, 2 will be reduced. So the outcome of C does not depend on D. The outcome of D does not depend on C. But however, they depend on the previous layer. So we are just seeing how this will impact. So if you look at it, now we have seen only one connection and how to reduce the, how to change the weight to reduce the error. So we need to look for all other weights. We need to figure out the deltas for all other neurons in the remaining layers. So the trick of back propagation is that we can use the neuron deltas at one layer to find the neuron deltas at the other layers. So far what we have seen is that we have seen how the delta is used to change the weights. And by changing the weights, what are we going to achieve? We are going to reduce the error, and thereby we are going to learn, the network is going to learn. Network is going to learn means it is going to reduce the error, and then it is going to make the correct predictions. For that, we are changing the weights and how C delta is used in changing the weights. So far we have calculated the deltas at the output layer, and we have seen how the output layer delta is used in changing these weights. So whatever we have discussed with A and C is applicable between A and D also, C and B also. So whatever is between the same link is applicable to the other links as well. So now let us see how are we going to, this is the third step in the back propagation. So what is the third step in the back propagation is that how are we going to find the other neuron deltas? So now we have the deltas values for the output neurons. We will use them to compute the deltas for the neuron layer just before the output layer. So we know the deltas for C and D. So now we are going to find the deltas for A and B, and we are going to see how using this one, we are going to find the deltas for this one. So using this, we have found out the weights for these layers. So now we are going to see how to find the deltas in the one layer before. How are we going to find? In a simple model, we just have neurons. In this one, we have neurons A and B. Let us now, like previously, we will understand only this connection. How using C, we are going to find A. The same thing can be applied to find out B also. So now we are understanding, we are finding only two neurons, A and C, and the connection between them is connected by the weight AC. So if you read this diagram from left to right, so you have the outcome of, so let's draw this one. So you have the outcome of A, and you have the neuron C, and you have the error here. So you have the outcome of A naught, and you have the output of C, and you have the total network error. So let us think that AM is the change in the outcome of A naught, sorry, A. This is going to be the change in the, this is not the outcome. So this is the outcome. This is the change in the outcome. This is A naught. This is AM, how much change it has. So this will get multiplied by AC, and that gives rise to the change in the outcome of C. So this is C naught. This is change in the outcome. So
AC, I mean, sorry, madam. AC gets multiplied by the entire AM plus AO, no, madam?
no, only the change in the outcome.
Oh.
So I will write it better. CM is equal to AM into AC. Okay. EM is equal to PM into C delta. So the change in the outcome into C delta. So let's understand here what we are trying to do. We are trying to find out the delta value for A. We have only the delta value of C so far, that is present here. Okay. And we know that the change in the outcome into C delta is going to give you the change in the error. So this was the previous error. This much it was the previous error. Now the error is reduced. So the current error is this much. So is the network error portion clear? So previously you have, so this was your previous error. So this is the change in the error. So this gets subtracted. The change in the error is negative. So this gets subtracted and the new error is this much. Is it clear?
This is clear, man. Left hand side, this AM into
Okay,
AC.
let's go step by step. So
Yes.
this is what we are seeing in this diagram. So the previous error gets reduced by the change in the error. The change in error is negative. So it is reduced and the new error is reduced. We have a reduced new error. This portion is okay. Now let us see this. So change in the outcome into C delta will give you the change in the error. So this is the neuron outcome. So previously it was still this much. Now the outcome has changed this much. The outcome has increased. So the change in the outcome is this area. So the change in the outcome into C delta will give you EM. So here both the signs are opposite. So if both the signs are opposite, this sign will be negative. So CM, this is this portion clear? CM into C delta, change in the network output into C delta will give you EM. Is it clear?
Yes, ma'am.
Now what is our aim? We have C delta. We need to find A delta. A delta is not present. Only C delta is present. What else is present? AC is present. That is the weight. So here we have an outcome AM. The change in the outcome multiplied by AC will give you the change in the outcome by CM. So how I am saying why AM into AC? So previously you had this outcome. You had this outcome C naught, A naught. So A naught is the outcome here. AC is present here. So A naught into AC will give you the C naught which is coming here. Now something has changed. So the outcome of A is changed by something. So how much it is changed? CM. Because of the change here, something has changed here. So this change in the C in the outcome of C is due to this change in this one. So AM into AC is equal to CM. Is it clear?
Yes, ma'am.
So if you look at here, AM into AC is equal to CM, and EM is going to be CM into C delta. So I substitute CM in this equation. This is the equation 1, equation 2. Substitute 1 in 2. So EM is equal to AM into AC into C delta. If suppose, let's have a small example. If AM is equal to 5 by 4, AC is equal to 1 by 5, C delta is equal to minus 4. So EM value will be 5 by 4 into 1 by 5 into minus 5. It's minus 4. So we have minus 1 is EM. CM value is AM into AC. So CM value is 1 by 4. EM value is minus 1. So the error is changed by minus 1. So we know that neuron C adds this together. So this is the combined equation. So in the combined equation, if you look carefully, this EM is equal to AM into AC into C del. So previously, if you look at here, the change in the error is going to be the change in the outcome into delta value. So this is still change in the error. The change in the error is equal to change in the outcome into delta value. So EM is change in the error. Change in the output is AM. So the whole thing which is left out is delta. So A delta is equal to AC into C delta. Is it clear?
Ma'am, last thing, ma'am. How did you get A delta? Sorry, last.
So 1 second.
I understood up to EM into AM into AC into C delta.
So did you understand this point?
All this thing, last line, the last. How did you
Okay,
get A delta?
we'll take one more step and we will go there. So if you look at here carefully, so now what I'm trying to do is that, so till this formula, it is clear. So from here, so this was the whole setup. We only had C delta. So change in outcome into C delta is change in error. So CM into C delta is EM. So this is represented here. Perfect. And now we have C delta. We don't have A delta yet. So what we have is a change in the outcome of A into AC. That will give you CM. So CM is equal to AM into AC. So we substituted both the things and then we got EM is equal to AM into AC into C delta. So now if you look at carefully, so what we can do is that EM is equal to AM into AC into C delta. I'm removing C. So here we had the neuron C. So now what I'm doing is that I'm straight away connecting for what change in the network error. What is the contribution from A? I'm straight away removing the neuron C from the picture. From the picture, neuron C is removed. And then I'm straightly connecting that AM into AC into C delta will give you EM. So here I am reducing this term. So this term is reduced. And here, this is the error which is reducing. So is this diagram clear?
Yes, ma'am.
So I'm just drawing this equation as a figure. So this is the change in the outcome. So change in the outcome is given by the into this particular value will give you the change in the error. So what is the thing? So change in the error is nothing but change in the outcome into delta value. So change in the outcome is AM. So, and the rest of the thing is delta. So what is this delta? This is the delta which is coming from A. So
But,
this is
ma'am,
A delta.
AC and CS is both delta now.
Sorry?
Now, AC and C delta is combinedly it is becoming delta AS.
Yeah. So A delta is nothing but AC into C delta. So
Yes.
what we saw previously, we are going to use the output delta to find the deltas of the remaining layer. So from the C, we are trying to find out the delta value for A. So C delta into the weight which is connecting A and C is A. A delta. Is
Yes,
it clear?
got it.
So still this formula holds good. The change in the error is going to be change in the output into delta, which is going to be your A delta.
Yes, ma'am.
If you look at here carefully, is it clear or confusing?
Good. By pictorial, if I correlate with the picture, I can be able to correlate. I'm
You are able
connecting.
to understand.
This AM and considering the change in output, considering AC into CS as a overall as a delta. So output change in output
This is
into delta
change
is
in the
equal
error,
to,
this is change in the output, and this is the overall delta.
yes,
So this is the thing. So the delta here is AC into C delta.
delta. Yes, ma'am.
So
Got
we
it.
are removing C from here. So straight away, how this A is impacting the change in the error. And
Got it.
in interiorly, if you look at it, C delta is helpful in finding out A delta. So first we have to find C delta, and then we have to find A delta. So this is what is back propagation algorithm. Back propagation algorithm means from the back you are coming. From the back, first you found out deltas for the output layer, and then using that output layer deltas, you are going to find the deltas for the hidden layer. So now we have found the delta. So, and still remember, we are looking only at one edge. A into C, A and C. This is the only connection we are looking at. We are not looking at into the other connections. Is it clear?
Yes, ma'am.
Okay. I'm not going to confuse you with so many other details. In next class, we will see how D will be added to this one and how other delta values will be computed and how the total delta, what is it? How the delta values for other layers and the change in the network error, combining all the neurons, we will see that one.
Sure.
So what we did in the previous class, we found out the deltas for the output layer. And now what we did is that using the delta, we did two things. Using the delta, how we changed the weights. This is one thing we saw. Because the change in the outcome layer can happen because of the change in the outcome from the previous layer and the change in the weights. So now what we used, we changed the weights and then we reduced the error, because reducing our error is a whole game. And how are we going to do that? We are going to do it by changing the weights. So now using the, now so far in hand, we only have the output layer deltas. So using these deltas, how can we change the weights? So that one we saw that, and how using changing the weights, we can reduce the error. And then what we did is that to find out the deltas for the remaining layers. So we have the deltas for the output layer and how we can use it to find the deltas for the previous layer. From the tiny neural network, we took only one connection and then we saw how one layer is connected to the other layer, how C delta is helpful in finding out the A delta value. Is it clear?
Yes, ma'am.
Okay, if it's clear, we will continue from the same derivation. We will continue how the other neurons will have impact on A delta. We will see it in the next class. Thank you.
Thank you.
Thank you, ma'am.
Thank you, ma'am.